lecture. So we'll continue with Möbius mu function in a moment. So let me briefly mention one of the homework problems some people have been asking me about. So it's to show this, some kind of congruence like this, and the comment is that 561 not a prime. So when I say standard and non-standard, so this is a non-standard question because I didn't tell you how to solve it. Like we didn't have something similar in the lectures. As opposed to what would be a standard problem is things like I did tell you how to do the lecture. Like if you had to do 5 to, I don't know, 15th mod 11, this one I did tell you how to do. Yeah? So it's a prime, there's Fermat's theorem, right? Okay, so this is the difference. So the non-standard problems, they mix various things like this. So you see, the hint is that this is not a prime. So of course, because we do number theory, the first thing to do is factor this out into primes. Yeah? That's kind of obvious, because that's what we do in this model. Okay, and then, so the hint is, as soon as you factor it, one needs to combine Fermat's theorem for each factor plus Chinese remainder theorem. And then it becomes a little bit standard because we did do things like this. For example, when we did RSA, we did Chinese remainder theorem plus Fermat's theorem together. Right? Okay, so now it becomes kind of standard with this perspective. So you factor this, you try to work with every prime and see what happens. But that's not a super difficult, not a super easy question, so one needs to do a little bit of work here. And I can give more hints actually, if people ask me by email. But I think that's a good starting point. Okay, so we are back to the Möbius mu function. That's the third out of the 4 functions we introduced. So we'll talk a little bit about this, and then we'll talk about Euler phi function. Okay, so I rewritten the definition once again. So last time I was using square free, not square free, and I realized maybe it wasn't very clear. So square free means that you are not divisible by a square. All your prime factors are different. And not square free means that you are divisible by a square. So last time I was writing it like this. P squared divides n. Okay, so if this does look a little bit strange, so how do we make sense of it? We just compute some examples. So mu of 1 is 1, that's in the table. Now mu of 2 is a prime, so we have 1 prime here, so we put minus 1 to the first power, which is minus 1. Similarly for every other prime, we have minus 1 to the first power. These are square free. Now 4 is not square free, so we are here, we are divisible by a square, it's 0. Yeah? So 5 again is a prime, so we are in the same situation as if, oh sorry. Okay, and finally 6 is slightly different because we have 2 times 3, so it's minus 1 squared because there are 2 prime factors, so it's a 1. And also it makes sense that the function is multiplicative, so this times this gives us this, so it is a multiplicative function. So all the values are plus, minus 1 or 0. Yeah, that's a function. Okay, and what I was telling last time is we can look at, so as soon as we have any function like this, we can look at the summation over divisor business. Okay, let's just do one example of this. I want to do m of 6. So I need to sum up over divisors. Divisors are 1, 2, 3, and 6. So I need to do mu1 plus mu2 plus mu3 plus mu6. Okay, and here are the values. So 1, negative 1, negative 1, 1. Altogether that's a 0. Yeah? And okay, so this looks like a coincidence, but in fact that's something we can now prove easily. And this is the next result. So proposition m of n has the following form. And it's not that this function is super important for us at the moment. It's more like demonstrating how certain method works. basically controlling these values, we also control the summation over divisors values. And the answer is, basically it will be always 0. So it's 0 for all n bigger than 1, and it's 1 when n is equal to 1. Just like this. Okay, so kind of, so here is what we always do to solve a question like this. We use multiplicativity theorem from last time. Multiplicativity theorem was telling us the following. As soon as the original function is multiplicative, and it was multiplicative, this implies that this summation over divisors is multiplicative. The advantage of being multiplicative means that we only have to concentrate on prime powers. So we say consider m to the p to the power k. Yeah, and so please pay attention to this proof, because that's the standard technique and we'll use it later today, and maybe I will ask you what should we do in similar situations. Okay, so we look at prime powers. Okay, so this is sum of mu of divisors of this guy. This is the definition, sum over divisors. And a trick we often use is we know what are the divisors of this guy. So I need to take mu1 plus mu p plus mu p squared all the way up to the last one. These are all my divisors. And now, you see most of these guys are just 0, because they are not square free, they are divisible by a square. Except for these two, which is -1 and 1. So you see altogether it balances out to 0. So here there's a little subtlety, so I want maybe k starting from 1. So I want to have at least 1 prime here. Right? So if I have, yeah, so if I have k positive, I have this, and the rest is 0. And also, we always have to do this case separately. So kind of, no, not all. Okay, so just it doesn't belong here because, okay, let's see what happens for m of 1. M of 1 is mu of 1. There's only one divisor here, so it's a 1. So we have verified this case, which wasn't a big deal. And we have checked this for prime powers. So we see that this is true for prime powers. So proof continued here, so proof continued. So it's almost finished, basically. M is multiplicative. So if n is a product of prime powers, which is non-trivial, so I mean n is not, so, right, so n is bigger than 1, so I have some primes in here. Then m of n is the product of those guys, so m of p1, k1 up to pr, kr, and now you see just all of them are 0. As soon as we have a single factor here, by this computation, each of them is 0. Yeah? So this finishes the proof. We use multiplicativity and control the prime powers. Okay. Yeah, so kind of this was a demonstration of a method how to control functions like this, but also there's something called Möbius inversion formula. So this was a Möbius function, and it's used in the Möbius inversion formula. So it's migrated from the lecture notes to the problem sheets in the week 3 problems. So the statement used to be in the notes, I used to be proving it, but I decided it would be better just to leave it. Okay, so it uses mu of n. And that's why I bring it up here. Okay, so this is done. All the values are 0 except for the one. It's kind of fun, I don't know. Let's see. So now the fourth function we studied. And the one we'll keep using in this module is the Euler phi function. Yeah, that one was Möbius mu, and this is Euler's function. So Euler was one of the founders of number theory, and lots of results are due to him. Right, so let's see. So we start with the definition. And then we investigate this function from different perspectives. Okay, so what's the definition? Right, so n starts from 1, then phi of n is the following thing. So I'll write something in words. So it's the number of integers from the list 1, 2, up to n, which are, so at the moment there are n integers, and I want those that are coprime to n. Okay, so here is a rule, definition, number of integers in the list which are coprime to n. And one thing we can do, we can compute some values of this function to make sure we understand what is the definition saying. So examples. Phi of 1. Phi of 1, we look at the list consisting of 1, and 1 is coprime to 1, so it's 1. So I can also comment about the list. So the list consists of 1 entry. Now phi of 2. We have list 1, 2, and 2 is not coprime to 2. They have a GCD 2, so 1 is the only one. Phi of 3. So I have 1, 2, 3. 3 is not coprime to 3, but the other guys are coprime to 3. Yeah? Okay, now phi of 4. So I have 1, 2, 3, and 4. We are looking at the ones which are coprime to 4. So 4 is not, 2 is not. GCD is 2. But the other guys are coprime. Yeah, and so on. So you see, at least given any n, we can compute it somehow. Just cross out the ones we don't want. So let's put it on the next level. Let's try to generalize a little bit this story about primes. So observation. Phi of p of a prime is easy to compute. Indeed, because what we have to do, we have to look at all the numbers up to p, and then we have to look at the ones which are coprime to p. So and the claim is, and this we've used this before, is that as soon as p is a prime, which is what I need here, all the numbers less than p cannot have any common divisor with p, just because their divisors will be less than p. So what I'm saying is that all these guys are coprime to p. Just like in this case. So 3, and the smaller ones were coprime to 3. Therefore, what we see from here is p minus 1. Yeah, so all of them except the last one are coprime. Yeah, so it's a bit of kind of mathematical investigation. So we're given a formula, we do some particular cases, we try to generalize. Okay. So for example, I see that phi of 11 is 10. Okay, so later on we'll see how this function is useful, but at the moment, so the good pure mathematics just concentrates on trying to develop some theme and see where it goes. Okay, we discussed multiplicativity, and the functions we are using are multiplicative. So after all, we'll be controlling primes and their prime powers, and then putting them together. So that's the next statement I'd like to make. So it's phi of a prime power. So you see, the observation was that phi of p is easy, and it was just this. And phi of a prime power is also not super difficult, but it's a bit more difficult, so it has a... Yeah. So we need to spend some time proving this. So basically the formula is this. So it's p to the k minus p to the k minus 1. And sometimes we can write it like this if we want. It's p to the... So some fraction of this. Yeah, so I can write it like this, or like this. So note that, of course, when k is equal to 1, what we get is what we know already. So, yeah, a particular case of this is p minus 1. Yeah? Okay, so let's prove this. So it must be something similar to what was happening here. We're thinking of our list, and we want to see which numbers we want. So what we need to find out, we need to count integers. So they belong in this range from 1 to p to the k. And what's the condition? Such that they are coprime to this. So GCD A and p to the k is 1. That's what I have to do. Yep. So now some observations. So we can think, what does it mean to be coprime to a prime power? So note the following: that GCD of this guy is 1. It's if and only if. You see, I want to have no non-trivial common divisors. And all the divisors of this guy are prime powers of the same thing. So it's the same as to say that P is not a prime factor of A. Or prime factor or prime divisor. So in symbols we can say P does not divide A. Yeah? Being coprime with a prime power, it's the same as being coprime with the prime itself. Okay, and now there's this principle. So it's a bit like in probability theory, so we are trying to compute certain probability, certain number of outcomes. And there are good outcomes and there are bad outcomes. And maybe good for us means this, and bad means, so the other case, when P does divide A. And sometimes it's easier to compute the complement and then see what's the remaining number of outcomes. So we do that, we look at, so we consider the opposite situation. The case when P does divide A. Yeah? And count these first. So all the integers in my list are either, let's say, red or green. And maybe red means this, and green means the other way, and controlling green is the same as controlling red, and the other way around. So what I suggest is we do count those guys, and then take the complements. Yeah? Okay. Okay, and then take the complement. Then take the complementary set. Okay, so let's do this. Now we need to make some observations again. So P divides A. It means that A is P times B. Yeah? That's the definition of what does it mean for an integer to divide an integer, where B is a positive integer. These were positive integers, so P is also a positive integer. And now also to make this work, we need to see how many B's there are. So our A belongs to this list. And therefore, we can see the possible highest value for B. Right? So, and our bound on A was this. So dividing through by P, our bound on B will be this. Yeah, so A is P times B. And therefore, from here, it's the same as to say this. So basically, I'm looking at all parameterization like this, where B is bounded above by this guy, but also it's bounded below by 1. So we have, okay, I'll write it here. So we have A is P times B, and B is from 1 to the previous power. Yeah? So if I want to look at all the integers in this list which are multiples of P, they will all look like P times an integer which is sitting in this bounds. Okay, so therefore the number, the set of A which are in the bounds we look at, and P divides A, has cardinality, so has this many elements. Just because here is how we parameterize all those elements, and B is uniquely determined by A. Therefore, okay, and we are almost done, so hence the complement of this set, which is now the red ones. So P doesn't divide A, has. Okay, and now we need to compute. So the total number is this minus the ones we don't want. So it's Pk minus Pk minus 1 elements. So this is the total number. These are the ones divisible by P, and the difference is what we want. So phi. So by definition, we're counting this, and we get this many elements. So this formula is done. Okay, so the next result is putting everything together. So we want to say that phi of n is multiplicative. So the usual kind of two things. So first multiplicative, and second the formula. So phi of a prime power factorization will have a nice formula. Just as for sigma and tau last time, which was yesterday, we put these things together for all primes. So I have P1, K1, So the first term times lots of other terms times the last term. So primes go up to R, and this exponent is going from K1 to Kr. Okay, and so how do we prove this? Or maybe again, before proving this, let's make an example. And just like yesterday we did sigma and tau of 180, we can do phi of 180. And if you think of this, it will be quite a lot of work to list all integers from 1 up to 180 and look at those which are coprime to 180. So this is really the way to go. So we can factor it as we did yesterday. So what was it? 18 times 10. 2 times 9 times 2 times 5. 2 squared times 3 squared times 5. And so 5 of 180. So we use this formula, right? So we have 2 squared minus 2, 3 squared minus 3, and 5 minus 1. This was phi of 5, the number of, so 1, 2, 3, 4. Okay. So 4 minus 2, 9 minus 3, and 5 minus 1. So it is 24, 48. So there are 48 integers up to this coprime to 180. Or we can do the other way. So of course, the one joy of mathematics is to get the same answer in different ways. So different way is would be to write 180 as, so what could we do? 9 times 20, and now phi of 180 is phi of 9. So of course I want this to be coprime. So when I mark your exams, and some of you don't make a coprime factorization, I get really upset. So we need them to be coprime, otherwise nothing works. So phi of 9, according to the formula, that's 6. We already had this. Okay, and maybe phi of 20. Okay, let's show off and let's just list all of them. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, let's do this. 10, 11. Okay, let's do this. 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. And I cross out the ones which have divisors 2 or 5. So all the even ones are gone. Yeah, sorry, this is not very legible, but you can imagine what I'm doing. So all that divisible by 5 are gone. And then the remaining ones are 1, 3, 7, 9, 11, 13, 17, 19. So let's see. 1, 2, 3, 4, 5, 6, 7, 8. Exactly. So it's 6 times 8. 6 and 8, which is 48, right? So everything makes sense. Yeah? So same answer. Okay, now let's think how we would prove this theorem. And again, there are some easier parts and some more difficult parts. So for example, what's the easier part? That 1 implies 2. So if we know that it's multiplicative, we know this formula. So assume 1 and let's prove 2. But that's the same as we did yesterday with sigma and tau. So I have phi of, so basically we open up phi by multiplicativity, what I called last time easy induction on the number of factors. phi of the first one, dots times. And now we use the lemma. The lemma where we did phi of a prime power. And so we get exactly what we want. So the first, yeah, wait, sorry. Okay, let me just make an error. So therefore we get this formula. Yeah, multiplicative open up, use each formula and we're done. Right, and what we have to do now is to check that phi is multiplicative. And this is a non-trivial statement that requires some work. Okay, now we prove 1, which is phi is multiplicative. So let's recall what this even means. It means the following. It means that we are given coprime n and m. We have phi of nm is phi n times phi m. And we can think what it means. It means that we are counting. So here we are looking at integers from 1 to n times m coprime to n times m, and here we do something similar for each of them. So it's not very clear how they are equal. They are related, but how do we see that they are equal? And one can do it directly by making a certain table which contains this many integers where there are n rows and n columns and do something explicit, and we'll get this out. But a more elegant way is to use Zn, so the residues modulo n, and Chinese remainder theorem. So it should look a bit like Chinese remainder theorem because n and m are coprime, and we are thinking about numbers in certain list, which looks a little bit like this. So what do I mean by Chinese remainder theorem? I mean the form I explained after I formulated it. Namely, it was saying the following thing. So n and m are coprime. There was this bijection between integers modulo the product and pairs of integers, where one is mod n and the other is mod m. So it's a Cartesian product. So this guy sends an element a mod n times m to the pair where the first one is mod n. So I have this class, and I reduces mod n here and mod m here. So you should remember at the moment how I spent some time explaining how Z15 is the same thing as Z3 cross Z5. This was the story. Yeah, so that's a map, and this map is a bijection. This is one way to state Chinese remainder theorem. Given two remainders here, there's a unique way to recover a remainder here. Yeah? So I have this identification, and I want to relate my equality that I'm checking to the two sides of this bijection. So to do this, I also need to make sense about this coprimeness condition. So I need to relate being coprime to n to property of an element in here. And we already know how this is done. So recall that A inside Zn is invertible if and only if this is coprime to the modulus GCD. So we did this in week 1 when we did Euclid's algorithm, linear congruences, and this was one of the linear congruences we're solving. So invertible means there's an inverse, and that translates into a linear congruence, which translates into representing 1, which translates into this property. This is something we've seen before. Okay, and now, so therefore, so here is the key observation. Therefore, phi of n is the number of invertible elements in Zn. So why is this true? So you see, typically we write these elements from 0 to n bar, but I could just as well write them from 0 to n minus 1 bar. I can write them from 1 to n bar. These are my elements here. Just this is equal to 0. And now what I'm saying is that one of those guys is invertible if and only if its integer is coprime to n. Therefore, another way to define this phi of n is to look at all the elements here which are invertible mod n. Yeah? So so to proceed with this proof, we need to introduce some notation which will be very useful later on. So we write Zn star. I think I haven't introduced it yet. So Zn star is the number, so the set of elements inside Zn such that A is invertible. So I'm looking at those guys which are coprime to n. And now with this, in this language, phi of n is nothing but the cardinality of this. Yeah, so this is this modulus sign means number of elements in this set. Another notation which I'm using, but maybe I haven't mentioned before. Okay, and you see we are almost there, because now we have to look at Zn, Zm, and Zn times m. So how do we proceed? So we proceed as follows. We say that Chinese remainder theorem in this form between classes mod n, m, mod n, and mod m, it induces a bijection, provides a bijection on the level of invertible elements as well. So I have Z and M, and I want to put a star everywhere. I want to put a star here, here, and also here. So I have this bijection which sends an element to its classes mod n and mod m, and I want to say that if I put a star here, its image will lie star here, and it's still a bijection. And so we need a little bit of explanation here, so maybe I can say because A is coprime to n times m if and only if A is coprime to both of them, to n and coprime to m. So I'm having this map, it's a bijection. I want to say that if I have an invertible element here, it goes to invertible elements. And this fact is, if it's coprime to the product, then it's coprime to each of them. And conversely, because n and m are coprime, being coprime to each of them means that this element is coprime to the product. Yeah? So that's something to think about, but I'm not sure I should spend much time explaining this. So basically, we can restrict to invertible elements on the two sides, and we still get a bijection. Okay, and now we're done. So there's just enough space to finish the proof. So now, just by looking at sizes of the elements on the two, sizes of the sets on the two sides, phi of n times m, which is the number of elements in number of invertible elements mod nm. This is left-hand side of this bijection. And now on the right-hand side, I need to look at Cartesian product of two sets. And one thing you know about Cartesian product is that the cardinality of it is just the product of the cardinalities. Namely, I need to choose one element from here, one element from here. Choices are independent, and therefore the total number of pairs is this times this. And now this is phi m times phi m. Yep. Yeah, so this is not a super standard proof, but it kind of explains how certain things which are non-trivial become simple if one uses enough language. In this case, the language was being invertible, this and this kind of set of invertible elements. Then what we are counting is simply basically two ways of counting the same thing. Yeah? This finishes the proof. So as I said, one could have given an elementary proof by putting everything in a table and computing things, but I think it's more kind of mathematical to do it this way. Okay, so basically we've studied everything we could about the Euler phi function. So we started with its values on the prime numbers. Then we did prime powers, and now we just know how to compute it for any positive integer. Okay, so also maybe let me say briefly how it is needed next week. So what we'll be doing next week is, and then we do something slightly different. So next week we're using Euler's function to prove Euler's formula. Euler's theorem. Euler's theorem. It will be that if I take, it will be the analog of Fermat's little theorem. It will be taking this power of A mod n. If GCT AN. So kind of what we should be thinking of is that we have Fermat's little theorem which tells us how to take powers mod P. And if we want to generalize it to arbitrary modulus, like P squared or P times Q, this will be the right power to consider. So we do this next week, so phi function we need to carry with us for next week. Okay, and in the remaining 5 or 6 minutes, what we'll do is we go back to the beginning. So we look at the summation over divisors. So that's a little kind of theorem we can prove. And here is when I'll try to ask for your input. So I'll see if you have been listening at the beginning of this lecture. So, okay, so as I've been explaining, one of the things we can do with these arithmetic functions is we can sum up their values over divisors. Yeah, so for example, mu function, we did this at the beginning of the lecture, or maybe sigma function itself was sum over divisors, and tau function was sum over 1s over divisors. But in any case, given such a function, we can form this new function by summing over divisors. And the theorem, again, which we'll be needing next week, is that there's a nice formula for this. It's simply n. Right, maybe let's just do a quick example for why this makes sense. So it looks a little bit surprising. So for example, let's take n equals 6 so that it's not super difficult. Then what I'm saying is that phi of 1 plus phi of 2 plus phi of 3 plus phi of 6 is equal to 6. So these are my divisors, and that's what I'm doing. So phi of 1 is 1, 2 is a prime, therefore it's p minus 1. Prime, it's 3 minus 1. Phi of 6. So I can think of whatever way I want. For example, I can say 1, 2, 3, 4, 5, 6, and I cross out the ones which are not co-prime. So basically 1 and 5. Phi of 6 is 2. Or you can also say 2 times 5, 3. So it's 6 indeed, it's equal to n, right? So it does work, at least in one example. Okay, and now the thing is, we need to think about how we prove this. And you see, at this moment what I claim is this became a standard question. So it's a standard thing. So this maybe was a little bit non-standard, but we've done some things like this. Standard check. And let's see if we can have any suggestions from the audience. So what could we do if we want to prove this? Yeah?
By induction?
So induction on what?
On n. Sorry, on d.
So you see, we'd like to check it for every n. And somehow maybe these functions are not quite, when you add n, when you do n plus 1, the function just changes in some weird way. So we don't really control this, but something like induction. So what kind of induction can we have here?
You split it into prime factors.
Yes, absolutely, yes. So it's kind of induction of the number of prime factors, sort of. Yeah, that's what we want to do. And the way to introduce some language here is just to give this a name. So if we want to study this animal, we should call it, give it a name. So this with its name, phi capital, sum of phi small d over d dividing n. And I suppose the suggestion was, if we have, so if we split n into prime factors, we use, basically we need to use multiplicativity theorem. So using multiplicativity theorem, this is the key. Namely, what we did just check is that this function is multiplicative, therefore this is multiplicative. So phi capital is multiplicative by multiplicativity theorem, therefore we can split its values into individual prime factors. Okay, and therefore what I have to concentrate on is each of those prime factors. And here will be another trick which I'll ask you about. Okay, so now I say consider, this is the standard business, so consider each of them. So how do we do this? Any suggestions? Again, once we understand what is the question, that's a standard procedure. So the question is, when our function is summation over divisors for this guy. Yeah? Anyone would like to tell me how should I compute this? So I suppose people know but don't want to tell me, so it's fine. So I just need to think what a divisor of prime powers, and we know this. So I need to do phi of 1 plus phi of p plus all the way up to the last one. This is what we can do. It's not difficult. And here comes the formula for phi. So phi of 1 is 1. Okay, phi of p is p minus 1. Now the next one is phi of p squared. It's p squared minus p. All the way up to the last one, which is, so here we use the formula for phi of prime powers, which we did some time ago. So we know all these guys, and this is a nice telescoping series, so we have everything cancels out except for the top power into the k. Yeah? And so now we are done, because now phi of of all the product. The whole thing is what is. It's just I need to do this for every prime power. So effectively I take identity function. Okay, so this is kind of a standard question. Okay, so I'll see you next week. So assignment is due next Tuesday, as I mentioned.